Hello, my name is Andrew Gary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. Listeners, we want to hear from you about why you love geophysics. Why did you choose geophysics? What do you love about the science and the work you do? We want to highlight as many of your stories in future episodes, so please email us your answers at podcast@seg.org or leave us a message with your story at country code 1-918-497-4627. SEG members, renew your SEG membership by December 15th and you could win a free book. Renew online at seg.org/renew. For this episode, we will explore applied geophysics from a non-technical professional's perspective. I am joined by Norm Hyne, who taught in the University of Tulsa Geology and Geophysics Department from 1969 to 1979 and was the chairman from 72 to 79. For the past 37 years, he has taught petroleum short courses at the University of Tulsa, helping non-technical professionals relate to and learn about geophysics. My conversation with Norm next. I have not yet had someone nod in understanding when I say that I work for the Society of Exploration Geophysicists. So let's start with the basics. How do you explain geoscience, petroleum geology, applied geophysics when you are asked?
You started with an easy one. Geo is derived from the Greek word for earth. Geoscience is the application of science to the study of the earth. In universities, they have geoscience or earth science departments. They're the same thing. And there are majors in geoscience departments in geology, geophysics, and less commonly in geochemistry. I am actually a geologist. It's the most common of the three. Geologists study rocks, the solid part of the earth, and the processes that affect those rocks, such as river erosion and deposition of sediments, both in the modern earth and in the ancient earth. Geochemistry applies chemistry to the study of Earth, and of course geophysics applies physics to the study of the Earth. There is also applied and theoretical geophysics. Applied geophysics has a practical use. For example, predicting volcanic eruptions, remote sensing the Earth from satellites or resources, predicting earthquakes, oil and gas exploration. An exploration geophysicist, who is what the SEG Society serves, explores for natural resources such as valuable deposits of petroleum and ore minerals such as copper and gold using physics. I am a petroleum geologist. I specialize in geological methods for exploring for gas and oil. A petroleum geophysicist also specializes in geological exploration. They use things like seismic, magnetic, and gravity to explore. Geophysicists find jobs in industry, universities, and government agencies. Now, in contrast, theoretical geophysicist works on something with no immediate practical use. A great example is in the 1890s, a geophysicist studying a large earthquake in the Himalayas. These waves pass through the earth, and he studied those waves, was able to determine the earth has a crust, an intermediate mantle, and a core in the center. Wow, that is no immediate application for practical use. Sure advanced our understanding of the earth. Studying into the earth is very difficult. We can't drill and sample, and we have to use earthquake waves. For theoretical geophysicists, they find jobs in universities.
Could you provide just a short overview of the various subject areas a geophysicist might specialize?
There's a great spectrum that they can specialize in, and I'm going to tell you some of my favorites. Number one is natural resource exploration. During the last decade, the oil boom was on. Most of the money spent by major oil companies, most technology advances were being made in the area of petroleum exploration and the subject of seismic. Seismic, very simply, is imaging the subsurface, seeing sound impulses are put in the earth, and they return as echoes to locate drill sites. Geophysicists also search for natural resources such as iron and copper. Ore minerals are very heavy compared to common rocks, and they distort the pull of gravity. And some are magnetic. They distort the Earth's magnetic field, and they can use variations in the Earth's gravity and magnetic field to find ore minerals. Another one of my favorites is an environmental geophysicist. They study the pollution of surface water and groundwater below the surface. They find hazards, such as potential landslide sites. They evaluate dam and construction sites. Very importantly, they find new water sources. Today, they have airplanes fitted with big hoop-shaped antennas that fly over an area to sense the electrical magnetic field to tell the difference between rock and water to a depth of 1,500 feet, about 460 meters below the surface of the ground. This has been used in Europe to find groundwater supplies and is now being used right now in Yellowstone National Park to trace hot water flow amongst the geysers. The SAG supports an organization called Geophysics Without Borders. These are volunteers that support humanitarian applications of geoscience throughout the world. One of the most important things they do is find water resources, places to drill wells in third world countries. However, not all the locations are in third world countries. They have several projects going on right now today in Australia. But my favorite type is a seismologist. They study earthquakes. Earthquakes are caused by faults. These are large breaks in rocks that make up the crust of the earth. Stresses build up along these faults for a period of time, tens of years, even hundreds of years, and the sides of the fault are locked by friction. But then the stresses reach limit of the friction, bang, the sides move either up or down, or sideways, or both. And that produces shock waves called an earthquake. There are stations throughout the world that record these earthquakes, and they very quickly determine the location, magnitude, and depth of that earthquake. The holy grail of seismologists is earthquake prediction. The greatest United States application in the San Andreas Fault that runs the length of California was right below San Francisco. In 1906, there was a very large earthquake underneath San Francisco. It did an enormous amount of damage. Most of the town burned down. In the 1970s, a big new fault was discovered offshore Oregon and Washington, the Cascadia Fault, related to the San Andreas Fault. It is capable of producing an earthquake that is much larger than the San Andreas Fault, along with a tsunami, and it is overdue. This fault was discovered by the work of geophysicists. The last earthquake on that fault was on January 26, in the year 1700. It was accurately dated by dead tree rings in the state of Washington. Because of the tsunami that earthquake produced and hit Japan, they know it occurred at about 9 p.m. at night, and it was about 9 on the Richter scale. Wow. Today, earthquake prediction is statistical. For example, they will say 25% chance of a 6 or bigger earthquake in the next 10 years. Another really big and unexpected application of earthquake prediction is nuclear test detection. They can actually tell the difference between earthquakes, nuclear explosion, and actually locate the site of that explosion.
My friends and family generally are happy when the cost of gasoline goes down. Could you explain how the cost of oil impacts the cost of gasoline and how these prices might impact the geophysicists?
Yes. Gasoline is made from crude oil in refineries, so the price of gasoline is directly related to the price of crude oil. That's the biggest factor. In a refinery, crude oil yields a little over 50% gasoline, with the rest being made into diesel fuel, home heating fuel, kerosene, tar, asphalt, and petrochemicals. Petrochemicals are chemicals that are sold to the petrochemical industry to make plastic, styrofoam, polyethylene that you wear, and drugs such as aspirin. Yes, aspirin is made 100% from crude oil. Actually, aspirin is an old Chinese remedy that is thousands of years old, and it was extracted from the bark of a birch tree. Today, with all the aspirin you people gobble, there'd be no birch trees left if they still made it from the bark. Pharmaceutical companies learned to make aspirin from benzene that comes from crude oil. But benzene is carcinogenic. It causes cancer. But because the chemical structure of the benzene is changed, it's safe to take. So when the price of crude oil goes up, the gasoline goes out to the gas stations and gasoline goes up. The United States used to export crude oil into 1948. But then we started to receive very cheap Middle Eastern oil. And that was right after World War II. That oil was coming in with these big super tankers. Saudi Arabia has the largest conventional oil reserves. OPEC was formed in 1960 to control oil prices. 1973, 1979, they withheld oil for political reasons. The price of oil spiked, and there were actually gasoline shortages here in the United States. OPEC lost control in 1986. That's because Nigerian oil, which is OPEC oil, was competing directly with North Sea oil, which is not OPEC oil. And when the North Sea oil price went down, Nigerians had to follow, and that broke the price control. The price fell from $35 a barrel to $8 a barrel in Oklahoma in 1986. This is very similar to the price fall in 2015 of a high of $110 to a low of $25 if you adjust it for inflation. It is very important also that you know finding and producing gas and oil is very expensive. It is very expensive to drill wells. In the United States, on land, it costs millions to tens of millions of dollars to drill wells, and that's much more expensive offshore, roughly 10 times the price it is on land. You should also realize that many wells are not successful. They're what they call dry holes, and you've lost your entire investment doing that well. In the United States, exploratory success rate is 40%. What does that mean? On the average, for every 100 exploratory wells you drill, 40 are successful and will produce economic amounts of gas and oil. 60 are going to be dry holes, and you lose your investment. Secondly, you ought to know that completing a well actually costs more than drilling the well, because you've got to run steel pipe called casing down the well, cement it in, install all that surface equipment. It's very important that you realize this, because exploration drilling is discretionary. Companies don't have to do it. During low oil prices, there's little or no exploration. Today, 2016, very little drilling is occurring on the land on the United States. One place they're still drilling is in the Permian Basin of West Texas. And that's because drilling costs are very low. They have several petroleum reservoirs they can drill through in one well. What they do in the Permian Basin is to drill a vertical well down about 7,000 feet. That'd be 2,100 meters depth. And then they drill several horizontal laterals into each pay zone. And then they stimulate each pay zone with hydraulic fracturing. And that makes it economical. Also, you should know it costs money to produce crude oil. I used to own oil wells back in the late 1970s and the early 1980s. And my wells in the early 1980s were making lots of money. I was being paid $35 a barrel minus a 1/8 royalty that I had to give to the landowner. My lifting cost, the cost that it cost me to produce 1 barrel of oil at that time, was $14 a barrel. So that was great. But in 1986, the price of oil fell to $8 a barrel. You must realize I was losing money. And at that time, I had to sell all my wells. So if you adjust that for inflation, that's a similar drop as occurred in the year 2015. Today's cost to produce that oil usually ranges about $40 to $70 a barrel. Many areas now have become uneconomical. There's a very famous oil play Well, the Bakken play up in North Dakota, it was big during the boom. Lots of jobs and lots of people moving to North Dakota. I just read a technical paper that no company make any money ever drill a well in the Bakken because that's a very expensive area, no pipelines leading to refineries. Oil has to be trucked out today, and the transportation cost is $18 a barrel. So no one's going to get their money back drilling a well in the Bakken. So during tight times, the oil producers have to cut back on their budget expenses. They have little or no profit. I read that $65 a barrel oil will stabilize the present companies. To the present, 2015 to 2016, 180 companies have become bankrupt. With low crude oil prices, companies are not drilling, trimming their employees, not hiring new geologists, new geophysicists. Low petroleum prices also affect oil company debt. 2016, ExxonMobil, Shell, BP, and Chevron had a total debt of $184 billion. That's twice the debt they had in 2014. And they had to get that money to fund their oil and gas operations. What actually caused the recent price drop in 2015 was drilling into unconventional oil and gas reservoirs. These are reservoirs, very low oil and gas flow rate through the reservoir, such as shale. The typical vertical well will be uneconomical. Production will be too low to justify that well. But today we drill oil and shales with new technologies. We use horizontal wells in oil and gas producing zones, and then we hydraulically fracture that zone. It's called fracking. And that greatly increases flow of gas and oil through that zone. These are called unconventional reservoirs. How they produce at an economic rate. The very first of these was a Barnett Shale that was drilled in Fort Worth Basin in the late 1990s. And that produced gas. Then we moved to the Eagle Ford Shale in Texas, and that had gas, condensate, and crude oil. Then the Marcellus and Utica Shales in Pennsylvania. Very big markets for that gas. And then the Bakken up in North Dakota. A lot of new oil was found. And America was heading to oil independence. Imports were going down. Saudi Arabia noticed this. They're the largest producer in OPEC. Flooded the market with more crude oil. Wow. There's only one thing that's going to reverse that. That's cuts in oil production. OPEC and Saudi Arabia. I think in the future, with less drilling that is going on today, the oil production will decline. Supply and demand will eventually take over, and the price of oil will go up. But geologists, geophysicists, and petroleum engineers are all very susceptible to large price fluctuations.
So, geophysicists in these companies don't solely work with geologists and geophysicists. They have to work with other non-technical professionals. So can you talk a little bit about how the geoscientists build bridges with the non-technical professionals that they collaborate with and depend on to be successful in their own job?
Yes, it turned out 50 years ago, all the older oil companies had separate geology and geophysics departments, along with other departments. And these departments didn't talk to each other. They just sent reports back and forth. But in a modern oil company, you're going to have teams of geologists, geophysicists, geochemists, petroleum engineers, and non-technical people all working together for a common cause, and they must communicate. They form one common report coming out of that team. Now, on these teams, you're going to have non-technical professionals, such as economists, who work the risk and reward of drilling a well, landmen that lease the land, and especially managers. Oh my gosh, they make the decisions, and many times they're not technical. So the team that you work with, you have to know why they're needed and the role they play in that team to make this process work. To do this, really, you should explain what you're doing in very simple terms. And to make it simple, don't use math. What I say is I calculate that. They're not interested in math. And also, if you're dealing with technical people, but not geophysicists, say using assumptions, because they like to question assumptions. Probability is also okay. Just like a weatherman says, 50% chance of rain tomorrow, you can say 70% of successful well.
So I don't want to take away from the course that you teach, but could you explain briefly the various ways that geoscientists explore for oil and gas?
Let's start with geologists. Geologists work with data from wells that have already been drilled. They make subsurface maps. And they get that data to make those maps, extrapolating from wells that have already been drilled. They also correlate well logs to draw cross-sections to an area. The best way geochemists can help you find gas and oil is to look for oil seeps. Natural oil seeps, oil naturally seeps in the surface of the ground, are very common. And many times you can see them in the La Brea tar pits of California. And many times there are micro seeps. Just a little oil leaks in the surface of the ground, you can't see it. So what a geochemist does is they sample the soil samples back in the laboratory, very carefully analyze the soils for minute traces of crude oil. Now for geophysicists, it's seismic, and that's imaging the subsurface using sound echoes. That's the major effort by oil and gas companies in exploration. That's where most of the money is being spent in exploration. In seismic, you put an impulse of sound down in the ground. They use a vibrator truck to do that. Then we listen for the echoes to return from the subsurface by using microphones that we call geophones. This makes a picture of the subsurface, the shape of the subsurface rocks, and we can use this to locate subsurface locations that are favorable for concentrating gas and oil. This technology actually started in World War I. That was an artillery duel. It was very important to locate the enemy's artillery. Both the United States, European countries, and Germany used physicists to locate the artillery by using sound ranging. That was applied to seismic after World War I was over. And the first oil field actually found by geophysics was in 1924 in Texas. They found it by using variation of gravity on the surface of the ground. First one using seismic alone was in 1928 in Oklahoma. But the problem with seismic, the sound traveling through the subsurface rocks is distorted by the rocks. Geophysicists must apply equations and enormous supercomputer processing to make an accurate picture of the subsurface. This is what they call signal processing. Now, I've heard, I'm not sure this is true, that the most computer capacity and usage of anywhere in the world, two sources. Number one, United States Department of Defense, sounds reasonable. Number two, United States geophysical companies. They do it with signal processing of seismic data. Sounds reasonable. What supercomputers do today, they can actually make 3D views of the subsurface. Wow, subsurface starts to look like a hologram. And it's like a 3D motion picture. The amazing thing, they actually published a paper back in the 1920s on how to do 3D seismic, but they didn't have the computers to do it. So the theory was always there, just so we had to wait to get these computers. The seismic is projected on a screen. It's 3D seismic. It doesn't do it any justice. These screens are two-dimensional. What the companies have today are 3D rooms. These are called viz centers. They actually project the seismic on the walls of the room. Sit in and you can actually look at the subsurface. One I really love for a viz center is called an immersive room. They project the 3D seismic on the wall, floor, and the ceiling. You walk into the room, you're literally inside the subsurface. Wow. They also have what is called 4D seismic or time-lapse seismic. What they do is they run 3D seismic over the same area at different times every 2 years. They then run it like a 3D movie. And you can actually see the oil being drained into the wells with time. Both geologists, geophysicists work together on interpreting the seismic. The geophysicists are calculating the layer velocities, and they give these to geologists, how fast sound goes through those layers. The geologists tell the geophysicists what the layers are composed of, sandstone, limestone, or shale. Geologists also tell the geophysicists what the shape of the rock should be, what is reasonable. They help in the interpretation of the subsurface.
You have lived and worked in Tulsa, Oklahoma for a long time. You're saying you came here to teach in 1969. When someone asks you about the earthquakes, one just this week happening in Tulsa, throughout Oklahoma, Texas, Kansas, even other parts of the U.S., how do you explain the potential causes?
Well, as you know, earthquakes are caused by faults, natural fractures in the rock. Stresses naturally build up over time, tens or hundreds of years, but the faults don't move because of the friction along the fault plane. Eventually, the build-up stress overcomes the friction, and that fault snaps. That produces earthquake waves. When I first moved to Oklahoma in 1969, earthquakes are not common. You can feel an earthquake when it has a magnitude above 3. And in the period of 1980 to 2008, Oklahoma averaged only about 2 of those earthquakes that had a magnitude of 3 during that time, and I never felt one. But in 2015, Oklahoma had 907 earthquakes, including 28 which are above 4. And we've had 5 biggies now. On September 3rd, 2016, Saturday, 7:05 in the morning, I remember this, we had 5.8 earthquake, and it lasted for 20 seconds. But here's the amazing thing. At the moment, November 6, 2016, last night when I was putting together these notes, we had an earthquake here in Oklahoma. Yes, it lasted for 15 seconds. It was a 5 on the scale. It was centered near Cushing, Oklahoma. You might recognize that name. That is a pipeline capital of the United States. Enormous amounts of crude oil stored in tanks. Fortunately, no tanks were ruptured because a spill of crude oil and fire that would result would be some major catastrophe. I lived in California for 9 years when I went to school. I felt only 1 earthquake, and that was just a 4. Now, most of these earthquakes in Oklahoma are not from this area. They're from around north central Oklahoma. That area is only about 70% of the total area of Oklahoma. Now, just recently in Oklahoma, we've had a lot of drilling in a new play called the Mississippi Lime Play. This drilling started at the same time the earthquake started to increase. And in the Mississippi Lime Play, you produce oil that is 75 to 90% water mixed in. That's a lot of water. And this is very salty water, up to 10 times more salty than seawater. You can't dump that on the surface of the ground. It'll kill everything. I've seen areas where accidental spills of this oil field brine on the surface of the ground has prevented anything from growing there for over 10 years. For economics, the very best way to get rid of the salt water, put it down, saltwater disposal well. Now, we also produce wastewater from hydraulic fracturing or fracking. What happens is, after they frack a well, hydraulically fracture the well, they backflush. They produce that frack water back up the well. That fracking wastewater is not as toxic as oil field brine. In an Oklahoma disposal well, 95% of the water that goes down is produced water, oil field brine, from oil production. 5% is frack water from hydraulic fracturing. How does this cause earthquakes in Oklahoma? The earthquakes in Oklahoma actually are caused by faults in the basin rock, which is located several thousand feet deep. The one I just felt was located at a depth of 5 kilometers, 3 miles depth. In Oklahoma and in many other areas of land, near surface is covered with sedimentary rocks, relatively soft, relatively elastic, sandstone, limestone, shale. They're underlain by basin rock at a depth of 5 to 15,000 feet. And basin rock is usually made of granite. You know that. That's the rock you used to make countertops out of. It's very hard, very brittle, and it's accumulating stress. Why is a basin rock of granite accumulating stress? No one's quite sure, but I think the reason is it's actually on a plate, the North American plate, which is moving to the west every 1.25 inches per year, which is 3 centimeters per year. That's causing the stress. Directly on top of that granite basin rock is a sedimentary rock called the Arbuckle limestone. It easily takes water from these disposal wells with absolutely no pumping. They call that on vacuum. That's not quite correct. It just means they don't have to pump. And the Arbuckle limestone is deep enough and that it's not going to pollute any of those near-surface freshwater reservoir rocks with oil field brine. And 1/4 of all Oklahoma disposal wells dispose into the Arbuckle. The problem is that water that's pumped into the Arbuckle limestone is getting down into the underlying basin rock. Those basin rocks contain already stressed faults. But the faults are not moving because of friction along the fault plane. What the oil field disposal well water does, it actually lubricates the faults. The water pressure forces sides of the fault apart. This overcomes the frictional resistance and the fault moves. What is happening? This water from oil production is being pumped down disposal wells into the Arbuckle limestone where it goes down into the basin rock. Their faults already stress on them, ready to move, friction holds them in place. The water lubricates the faults, pressure forces the fault sides apart, and the fault moves. Snap, you get your earthquakes. Now, the Oklahoma Corporation Commission recognizes this. What they've done is where you have areas of earthquakes, remember, there's only a small area in Oklahoma these earthquakes originate. They're shutting in or reducing injection of disposal wells in that area. And almost immediately, earthquakes decrease in number in that area. This has happened in other areas where they have earthquakes, but when they shut in the disposal wells, earthquakes stop. This has happened in Denver, where they have a Rocky Mountain arsenal that was disposing of water disposal wells. In Ohio, and in Texas, Fort Worth Basin, where they were drilling the Barnett Shale in the late 1990s. Now, it's very interesting. The 5 biggest recent earthquakes in Oklahoma are on the edge of the area where the water is being disposed. And at least one of the faults wasn't even known. What they postulate is that these big earthquakes are being caused by the pressure pulse going off from the disposal wells.
Do you have any tips for someone reading and searching for articles about where they can find accurate and reliable information?
Yes, accurate and reliable information is sometimes very hard to verify. Government agencies probably are your best source for truthful information. No, I'm not talking about politicians. But government agencies hire professionals, geologists, and geophysicists. And we all have a code of ethics that we follow. In Oklahoma, we have the Oklahoma Geological Survey. Every state in the United States has a geological survey. They hire professionals. They're always doing research. Right now in Oklahoma, they're putting up an earthquake detection network, and they're studying water pressure increases in wells, and they all imply geophysics. So let me conclude. Geophysics, very valuable work for our modern civilization. And sometimes they do really neat things exploring the pyramids. A geophysicist or a geologist that works in the industry are highly paid, but it's a cyclic profession. Unless you work for government or academia, it's more stable. But if you're like me, teach students, explore for hidden chambers and pyramids, that pays for itself.
During our exchange, Norm incorrectly referred to geoscientists without borders as geophysicists without borders. To learn more about Geoscientists Without Borders, visit seg.org/GWB. At seg.org/podcast, you will find all Seismic Sound Off episodes. Also at seg.org/book sale, save 60% on 12 titles in the SEG Bookmart. Visit seg.org/book sale to learn about the other 38 titles on sale for 25 to 55% off. Please subscribe to Seismic Sound Off on iTunes or wherever you listen to podcasts. If you enjoy this show, review us on iTunes. Your reviews will help others find the podcast. Season 1 of Seismic Sound Off is sponsored by the SEG Wiki, home to hundreds of biographies of key geoscientists, geophysical tutorials, and core content from the science of applied geophysics. Visit wiki.seg.org to learn how you can grow the world's first online geophysics encyclopedia. Original music by Zach Bridges. Special thanks to Stacy Baker for connecting Seismic Sound Off with Norm Hyne. This is Seismic Sound Off, signaling off.